Hello everyone, I'm Daniel from Sirocco, and I'm going to introduce you to some data types in Haskell. I'm going to talk about some basic mechanisms that allow the user to introduce their own data types in the programming language called Haskell. Let me start with algebraic data types. And moreover, this video is about algebraic data types mostly. The simple example of an algebraic data type is a type which is defined by enumerating some constructors with no values. Here is an example, the data type called day. It consists of 7 values, each of which represents a day, some day of the week. Informally, one may read that as follows. A day is either Monday, or Tuesday, or Wednesday, or Thursday, or Friday, or Saturday, or Sunday. Just 7 flags without any additional information. An example of a function written on the data type called day is a predicate called isTuesday, which is true when a given day is Tuesday or false otherwise. The second example is a little bit more interesting. This data type called point represents a kind of the Euclidean plane consisting of ordered pairs taken from double, where double is, very roughly, a representation of real numbers in Haskell as well as in any other programming language. Here we have 2 points. The point from the left is a name of a type. The point from the right is a data constructor, which is a function itself. Let's take a look at this line. Point is a function that takes 2 doubles and returns a point constructed or generated by these 2 doubles. And here's an example of a function defined on this data type. The function is called taxicab. This function computes the distance between 2 points using the taxicab metric from the taxicab geometry. Here we part mash on values of points. We take doubles from those constructors and compute the distance between those points using this formula taken from Wikipedia. The problem of the previous data type is that our points might store integers or strings, perhaps, if one needs to measure the distance between strings somehow, for some reason. So anyway, we have to generalize the point data type in the following way. We can parameterize this data type with a type parameter, where here a is a type variable that ranges over data types, if roughly. And as previously, we have 2 points from the left and from the right. The point from the left is a type function, and it has its own type called kind. This type constructor takes a type and returns another type. The last sentence is written down here on the last line formally using this notation, star, arrow, star. And star is a kind of a type, if roughly. And here we have a kind of function that takes a type and returns another type, as I have already said. But point from the right, very roughly the same as previously. It takes 2 values from A and returns points generated by those two values from A. So we have a kind of polymorphism in algebraic data types in order to make more general. The next example is related to field labels. The problem is that product data types are quite cumbersome occasionally. For example, we have this data type called person, and it stores 4 values: string, int, and float. The problem is that it's not so convenient to button mash on the values of person. The second problem is that we actually don't know what all those values do. We don't know what's going on with their semantic roles, something like that. And alternatively, we can define this data type called person in a more intuitive way. We have a record that has 4 fields, and all those fields are named. That is, all those fields have their own names. And here we have the additional information about all those values. For instance, the first string represents the first name of a person. The second string represents the last name of a person. Age is about is a field that stores an integer, or to be more precise, an element of int. And this field represents an age of a person, and the same for the last field called height, and this field stores the value from the data type called float. And moreover, all those names are also accessors. What do I mean by that? Well, we can take a person, a value of the data type person, and return values that this particular value of person stores. So, in other words, all those functions like first name, last name, age, height are a kinds of projections. So we take person and return its first coordinates that we call first name. And this mechanism makes our product data types perhaps more user-friendly. So finally, let us discuss a couple of examples taken from standard library as well. The first example is a type called maybe. Maybe is a data type of optional values. Why do we need that? We have a function called head. It takes a list and returns its first element. And again, we have a kind of case analysis, and if a list is non-empty, then we can extract its head and return its head. But here is the question: what do we have to do when a given list is empty? And the problem is that the empty list has no elements and it has no head in particular. And the head function, for this reason, is not total, and consequently it's unsafe. But we can make it safe using the data type called maybe. Again, we have a case analysis, and if a list is empty, then we return nothing. But if it's non-empty, we can take its head, called x, and return just x. Here is our final example. Here we have the data type called either, and this data type describes values with 2 alternatives. Either EA is either left E or right A. That is, we have either the left constructor that stores some value from E, or we have the write constructor that stores some value from A. Here's an example. Mathematically, this data type represents a kind of set-theoretic disjoint union, but I don't want to go into all those mathematical abstractions, so let us discuss only this quite simple example. We have the function called tail. It takes a list and returns its tail. The problem is that the empty list has no tail because it's empty. It doesn't have elements at all. Okay? So for this reason, the function tail cannot be total, and therefore it's unsafe. And we can redefine this function using the either data type, and we take a list and return either string or list of A, or some list of A. And here we have the case analysis with pattern matching similarly, and if the first argument is empty, that is, our list is empty, the empty list, then we return the left with our error message. I have no tail, please don't do that. But if a list is non-empty, then we can extract its tail from the const constructor and return write excess. Okay? The difference between maybe and either, at least according to our examples, is that if our computation is broken somehow, then we just return the flag nothing if we have some failure. But here we can use the left constructor that stores some additional information about our failure. This is the main difference between maybe and write, and either, I'm sorry. But all those data types are quite helpful when you write some real-world code. This is it. If you like this video, then you may subscribe the channel and click the bell icon to have more updates from our YouTube channel. And cheers! Many thanks indeed for your kind attention. Bye.